Yes. So what we have been discussing so far in the lecture? Yeah. What we have been discussing so far? Okay. So we till now, what is the essence of this course? Okay, what is the essence of this course till now? The if someone asks you what is the takeaway of this course, what is the takeaway of this course? So what should you answer? What's the takeaway from this course? Yeah. Can anyone? Okay. So takeaway of this course is regarding many concepts, but one of the most important is time series. Okay. So what about this time series? Suppose you are having a chaotic map. That means say the logistic map. We discussed the first map in our lecture, right? Xn plus 1 is Rxn into 1 minus xn, right? So what happens in this? What we did, we plotted the time series of this map. Okay. Suppose at some point your map like exhibits chaotic behavior. Chaotic behavior. What is chaotic behavior? That means sensitive dependence to initial condition. If there is a slight change in initial condition, there is a huge change in the outcome, right? So how can you understand that from the time series? Suppose you started at this point, or maybe this point, because this is n is equal to 0, which is the initial condition. This is the initial condition, n is equal to 0. So after n is equal to 0, maybe you went to n is equal to 1, then n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. Yes. So you see this is your time series, right? When you started from this point, this blue point, when you started from this blue point, yes. So now what we will do is suppose you started from a nearby point, that is this red point. Is red close to blue? Yes, red is close to blue. But this is a new initial condition, whereas this is another initial condition, right? So when you started from a nearby initial condition, what happens is initially it might look the same. Initially your time series might look the same, but slowly it will start to diverge. Okay. Slowly it will start to diverge and totally different from the initial case. Like, okay. So is red and blue the same? No. The time series of red and blue are totally different. Yes. But initially they might appear to be same. Okay. So this is the property of chaoticity. Okay. Chaotic. That means sensitive dependence to initial condition. Sensitive dependence to initial condition, right? So initial conditions, or it is known as SDIC, okay, sensitive dependence to initial condition. So this is regarding the time series. Okay. So normally in many well-behaved system, you normally don't see this feature. But whenever you deal with weather, whenever you deal with highly nonlinear systems, you see this time series behavior. Means the time series will depend on when you start, which point you start. So starting condition matters a lot. So therefore, these are chaotic systems. And this is the essence of this course. Okay. Now, in this lecture, we are going to understand this essence a bit more clearer or a bit more better. Okay. So normally you cannot always exercise the time series. Normally you cannot for any system see the time series and think whether it is chaotic or not. Yes. So for that you need a statistical measure. You need a statistical measure, or say like a quantitative measure, which can tell you that yes, the output, the output, yes, if it is positive value, then it is chaotic. Okay. Suppose it is negative value, it is maybe regular behavior. Okay. And if it is close to zero, it is quasi-periodic. Okay. So something like this, we need a metric or a statistical measure for this. Okay. So motivated after this, scientists thought about it. I mean, how we can understand, how we can frame a quantitative measure so that we can understand the chaotic behavior of the maps or of the system, of the dynamical systems, right? So after this, scientists came to frame a new statistical measure or a quantitative measure known as this Lyapunov exponents. Lyapunov exponents. Okay. So what is this Lyapunov exponent? So Lyapunov exponent measures the divergence, like divergence of the nearby trajectories. So when we told you that you start from this initial condition and again you start from this initial condition, I see 2, and what happens? This one goes like this, and maybe when you started this one will be maybe very irregular. Okay, so it can be like this, and it's the same system, same parameters, right? So how we can understand that it is chaotic? Of course, you can see that both of these systems have diverged. There is a lot of big separation, even though they started this close, but they are separated a lot. Okay, can we take the ratio of after p iterations? After p iterations, say after p iterations, this is the value, and this is the zeroth iteration, the starting point. Can we divide the value of p iteration by the zeroth iteration so that it can tell you whether the divergence is getting contracted or the divergence is getting expanded, right? Are you understanding the idea? You're getting, right? So this ratio which detects the rate of separation of orbits is nothing but the Lyapunov exponent. Okay. So this is what we will understand in this class. But before we go into detail, I will spill the beans. Okay, I will spill the beans. That means I will tell you what is the most important criteria, and then we can go on to understand how we are framing or getting to this quantitative measure. So suppose you have a 1D map. So Lyapunov exponent is valid for both. Lyapunov exponent short term is valid for both flows and maps. Okay, everyone can, each of this system can compute the Lyapunov exponent. Maybe it is a ordinary differential equation system or it's a recurrence equation system. In both cases, you can compute Lyapunov exponent. Okay, and okay, so for a suppose you have a 1D flow and you have a 1D map. In both cases, you will have only one Lyapunov exponent. Suppose you have a 2D flow and a 2D map, then you will have two Lyapunov exponents. Lyapunov exponents usually we write by lambda. So lambda 1, here you will have lambda 1, lambda 2, two different Lyapunov exponents. Suppose you have a 3D flow and a 3D map, then you will have three Lyapunov exponents. That is lambda 1, lambda 2, lambda 3. Okay. So therefore, can you tell me what does ND system mean? For an ND system, you will have n Lyapunov exponents. Okay. N Lyapunov exponents in the sense lambda 1, lambda 2, lambda 3, so on up to lambda n. So n different Lyapunov exponents. Okay. So now, how these Lyapunov exponents can tell us any information? Why are we computing? Okay, that's our question. So if in any of these systems, when you compute, so these collection of Lyapunov exponents you are seeing, this n Lyapunov exponents collection is sometimes known as the Lyapunov spectrum. Okay, this is the Lyapunov spectrum. Okay, is the Lyapunov spectrum. This means the collection of all Lyapunov exponents together, just like your eigenvalue spectrum, or right, eigenvalue spectrum. What does it mean? Collection of all types of all eigenvalues of the characteristic polynomial, right? So therefore, it is Lyapunov spectrum, right? So what is the use of this? So if in any of these systems, maybe it is one dimension or two dimension or n dimensions, if at least one Lyapunov exponent, that is lambda I, is greater than 0, that is positive, then the system is chaotic. So this is one of the most important results in dynamical systems literature. Okay, and one of the most important results also. So if at least one of the Lyapunov exponent is positive, then the system is chaotic. Okay. So now people will ask, okay, what happens if more than one is positive? What happens is if more than one Lyapunov exponent is possible. So suppose if in any system more than one, that is greater than one number of lambda i's is greater than 0. Okay, that means say lambda 1, lambda 2 greater than 0, or lambda 1, lambda 2, lambda 3 greater than 0, any number, then the system is even more chaotic. The system is even more chaotic, and we have a special name for it. Then the system is referred to as hyperchaotic. Fine. The system is referred to as hyperchaotic system, right? Now suppose there is another criteria, okay, that is if all Lyapunov exponents are less than 0, that means negative. All the Lyapunov exponents are less than 0, then the dynamics is regular. Regular means it can be either a fixed point or periodic orbits. Okay, it can be either fixed points or periodic orbits. Fine, that's the idea. Okay, now people can ask, okay, there still is another possibility. Now, what is that possibility? There is still another possibility that your system has very close to 0 Lyapunov exponents. Okay, that means some lambda I is very close to 0. I mean, say 10 to the power minus 4 tolerance. Okay, if your Lyapunov exponents, any Lyapunov exponents is very close to 0. Okay, I mean, you set a tolerance, it can be minus 10 to the power minus 5, it can be plus 10 to the power minus 5. In between that, any value that we will consider equal to 0. Okay, in between that tolerance, we will consider that value to be 0. And when that Lyapunov exponent is 0, then that behavior is something new that we will call that it's a quasi-periodic behavior. So quasi-periodic behavior, right? So in quasi-periodic behavior, you see Lyapunov exponent, at least one Lyapunov exponent will be close to 0. If one Lyapunov exponent, so yeah, we'll start here. Okay, maybe we'll go like this, maybe. Yeah, maybe we'll do it this way. If one Lyapunov exponent is very close to 0 and all others are less than 0, right? So it will be like quasi-periodic. But however, in this, you will see when you draw a phase portrait of this system, you will see a closed curve like this. You will see a closed curve like this. This curve is not a curve. This curve is made up of million of points. It is quasi-periodic means it is very near to periodic. That means suppose you start from here, then next point iterate is here, 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 right? Then again next point will be here. You see? Are you understanding how it is moving? Then next point will be nearby that. Yes? I hope we are getting that idea, right? So what will happen like this? You will soon cover the whole set of points. Okay. So this is a quasi-periodic curve. Okay. Now suppose two Lyapunov exponents are very close to 0 and others are less than 0. Others are less than 0. Then it will be still quasi-periodic. But however, since two Lyapunov exponents are close to 0, it has 2 degrees of freedom to move. Okay. So therefore you will see something like a torus. Okay, something like a torus. This is like a torus, like a donut. Okay, the behavior, the iteration behavior will be like on a torus. So all the iteration will fall on a torus. Okay, suppose 3 Lyapunov exponent are close to 0 in the system and others are less than 0. Okay, and others are less than 0. Then it will be still quasi-periodic, but it will be higher form of torus. Higher form of a torus. Okay, higher form of a torus. I mean, which we cannot visualize because it's already more than 3 dimensions. Okay. However, you can visualize it in a way. I will tell you a very nice way to visualize this is suppose you take a paper, okay, and place it inside this curve. What will happen? The curve will pierce inside the paper, right? So it will pierce the paper at only one point. It pierces the paper at only one point. So on the paper, what you see? Only one point. Yes, on the paper. Now, suppose you put a paper here. What you will see on the torus? On the torus, if you put a paper, what you will see? A circle, isn't it? You take your medu vada. You take your medu vada, right? And what you do is you slice it with a knife. You slice it with a knife and see it. So what you see? A white, dense structure, right? Yes. So, but here the inside part of medu vada is not there. Only the outside. Okay. So what you see? Only a circle. Only a circle. So what you see here when you put a paper? A circle. Yes. So now when you put a paper on the higher form of a torus, suppose you put a paper on the higher form of a torus, what you will see? When you put the paper, you will see a torus. You will see a torus. Okay. So it's a torus, like a donut. You will see a donut. Okay. How this happened? Good. I will change the questions. Okay. Did you see something? You saw. Oh, we will put more pages. Hmm. Yeah. Yeah. So, okay. So this is the higher form of a torus, right? Fine. Okay. So these are all possible behaviors you can have with the Lyapunov exponent spectrum. Okay. These are all possible behaviors you can have with a Lyapunov exponent. Okay. So Lyapunov exponent is a simple way to characterize the dynamics of a chaotic system. Okay. And we can start with general 1D maps. Okay. We'll start with general 1D maps. Now that you know the full idea of a Lyapunov exponent. Okay. So any system you are working with, usually computing Lyapunov exponent is one of the best ways to understand any dynamics of your system. Okay. So there are many methods to compute these Lyapunov exponents. Okay. So you can either use QR method, okay, where you take a Jacobian matrix and you do QR decomposition to that Jacobian matrix, okay, and keep on doing the decomposition till you get a diagonal matrix, with all entries. All the entries of the diagonal matrix will be the Lyapunov exponent. All the diagonal entries of the Lyapunov exponent will be the all the diagonal entries of the matrix will be the Lyapunov exponents. All other will be zero in a diagonal matrix, right? So more detail you can go into this method, but it is more of a research project. Okay, but I am telling you the ways through which you can still compute. There is something well known as Wolf algorithm. Okay, Wolf's algorithm. So this is this is very old algorithm, but very robust. Okay, so people still consider this in many applications. Okay, anyway. So what we can do is maybe the remaining part of this lecture, what we can do is we can frame how we are computing the Lyapunov exponent. How we are computing the Lyapunov exponent. And second, we will compute Lyapunov exponent of a 1D map. Okay. Shall we do this today? Shall we do this today? What do you think? These two things. Okay. So usually computing Lyapunov exponents is analytically challenging. Okay. Usually Lyapunov exponents we always compute numerically. Okay. And Lyapunov exponents is computed for a longer time series. The more longer the time series, the more accurate your Lyapunov exponent is. Okay. So therefore, since you will compute for a longer time series, what will happen? Your computation time also increases. So Lyapunov exponent computation is computationally hard. Okay. So therefore, usually what happens is usually we use cluster computing or like parallel computing to achieve this. Okay. So maybe what I can do is maybe if I have, I can share. Yes. So you can see this is one of the work. Okay, this is one of the works in which we have plotted on x-axis one parameter. This is a sine circle map. This is a sine circle map which we are studying, which you can read from the lectures anyway. Okay, this is suppose a map. It's a 1D map. Okay, what we do is on the x-axis there is a parameter omega, okay, and on the y-axis there is a parameter k, okay. Now what we are trying to do is we are varying the two parameters, and we are color coding each of the points with the color, with the value of the Lyapunov exponent. Okay. So here you can see the black color you are seeing are the periodic orbits. Okay. The black color you are seeing are the periodic orbits. Okay. And the colored regions you are seeing are maximum chaotic orbits. Okay. You can see there is a gradient of color. Okay. Some colors are bit light blue and some color are dark blue, right? However, most important, interesting part of this is this takes a lot of time to compute. Okay, this takes a lot of time to compute. So you can see that, yeah. So very nice high quality diagram has been shown, and of course it's a fractal. Of course it's a fractal. Okay, and the more and more you zoom in this area, the more and more you zoom in this area, you will see these tongs. Okay, these are known as Arnold tongs. Okay, the tongs you are seeing, right? So the this region here, you can see my cursor over here. This is a Arnold tong. Okay, you can see this is an Arnold tong, and it looks like a tong, right? It looks like a tong. And this Arnold tong is everywhere. It is here. It is here. Okay. And more you zoom on, zoom on, zoom on, those Arnold tongs will still be there. Okay. Infinite scaling. At infinite scales, they will be there. Okay. However you zoom, they will be there. You won't find a point where they won't be there. Okay. So that's the point of Arnold tongs. And these Arnold tongs are nothing but periodic orbits. These Arnold tongs are nothing but periodic orbits. Okay, these are periodic orbits. Fine, and it is interesting in the sense that the boundary of these Arnold tongs are pretty interesting. Okay, so what happens? Yeah, what happens in this? Yeah, maybe. Okay, so yeah, maybe I will draw it later. Okay, so what happens in an Arnold tong? Okay, so now what happens in Arnold tong? Let us see. So this is an Arnold tong, right? This is an Arnold tong, right? So what you see is this boundary. The outside, the tong boundary is nothing but a bifurcation curve that is known as a saddle node bifurcation curve. Okay, it's a saddle node bifurcation curve. It's a curve. Okay, and usually you will see that something like this. Okay, in the behind of the tong, this is usually period doubling curve. This is usually the period doubling curve. Okay, and most importantly, since these curves, the width decreases as you approach towards the end point, right? So this curve will be tangential. This curve will be tangential, okay, to another curve. Okay, so this curve is nothing but an Emax-Ecker bifurcation. Okay. So all these beautiful pictures you are seeing, which I just showed you the moment before, all are just not random. They are in such a way that the bifurcation curves are aligned. Okay. So the bifurcation curves are aligned in such a way that you are seeing these nice bifurcation diagrams. Okay. Like maybe you can see this again here. Okay. Again, there will be another tong, again another tong. In between these two tong, there will be another tong. In between these two, there will be another tong. Okay. How these tongs are separated? Any ideas? So the important thing is, suppose this is a period 3 orbit and this is a period 5 orbit. Okay. Inside this periodic orbits are lying. So if it is a period 3 orbit and a period 5 orbit, then in between the two, there will be period 8 orbit. What is 8? It is the sum of 3 and 5. Okay. Now, in between 8 and 5, there will be a period 13 orbit. Okay. Now, in between 8 and 3, there will be a period 11 orbit. In between 11 and 3, there will be a period 14 orbit. Okay. So, you see how these organizations are being done. Okay. So, therefore, when I want to show you now, you can better understand the diagram. Okay. So, let us see. Yeah. So, now you can understand it better, right? So, see this. Here, this periodic orbit is of period P1 Okay, suppose this periodic orbit is of period P1, this is of period P2, then this period will be P1 plus P2. Okay, this black one. And there is another guy here. Then there is another guy here. You see, okay, infinitely many places they are organized. Okay, so this is very famous for Arnold Tonks and very interesting. Very interesting. The moment you keep on spanning through. Okay, fine. So these are all about the Arnold Tonks and whatever structures, important structures we can analyze in a system. Okay, fine. So let us come back to our map. Okay, let us start with a 1D map. Okay, let us start with our 1D map. Okay, so what we will do, suppose our 1D map is given by say xp plus 1 is suppose f of xp. Okay, this is our 1D map. Fine. So obviously x belongs to a unit interval that is say 0, 1. Okay, we are doing this. And you know that suppose the initial starting point, suppose initial starting point is say x naught. So what happens? X naught, then x1, then so on x2, so on till pth iteration, and xp, then xp plus 1, so on. Yes. So this is how the iteration of the map works. Fine. Okay. Fine. So suppose like let us assume suppose there is a periodic orbit. Assume we have a periodic orbit. We have a say periodic orbit orbit of period p. Suppose period is p. So what is the expression for that? What is the expression of the periodic orbit? Suppose you started from x naught. So after p iterations, you will come back to again x naught. Yes. So therefore x naught is nothing but the xp. Yes. So what is xp? Xp x naught is xp, so xp is x naught. But what is another way of writing xp? I mean, how you how you can find xp? We are at x naught, then we went to x1, then how we go to x1? By applying the map f. After how we go to x2? By applying f to x1. Like that we go to xp. So what should be the formulation of xp? Xp is nothing but f composed p times of x naught, isn't it? F composed p times of x naught, right? Do you agree? Yes. So what does it tell us? That if you start from x naught and you iterate p times the map to x naught, you come back to the same point x naught. Yes, that's a periodic orbit, right? I hope everyone remembers. Hmm? Fine. Now what we want to do here, okay, what we want to do here, suppose we want to analyze a small deviation. That's what we are doing here, right? So I told you, if your orbit is chaotic, what will happen? If we take nearby initial conditions, the time series will diverge. The time series will diverge, right? So let us take one small deviation. Let us take one small deviation to the point, okay? So say like we started from x naught, okay? Then you went to this iteration. This is the xp minus 1 iteration, and then when you iterate it back, you come back to the point xp. Yes. So now what I want you to understand is, suppose we disturb the point x naught. Let us disturb the point, or perturb scientifically, perturb the point x naught to a new point, that is x naught by some delta. Yeah. Can we perturb the point x naught by adding some value delta? Then it will be delta means it's a very nearby perturbation. I mean nearby displacement. Fine. Do you agree? So if I disturb the point x naught by delta, the final point will also be getting disturbed, right? Don't you agree? If the initial point is disturbed, the final point will also get disturbed. So suppose the final point is getting disturbed by say xp plus delta p. When your initial point is x naught, final point was xp, right? Fine. So when you took suppose delta naught, when you add this perturbation delta naught to x naught, another perturbation can occur to the final point xp, but it won't be the same perturbation, right? I mean generally. So it will be delta p, write xp plus delta p. Do you agree? Yeah. So what can we write now? What can we write now? We can write, say, x naught plus delta naught is nothing but fp of xp plus delta p. Yes. Yeah. Isn't it? It's a periodic orbit, right? It is not chaotic. It's a periodic orbit. Any issues? See, it is a chaotic orbit, then this might not be applicable or might be difficult because you cannot predict the F composed that it will return back. But since, suppose you said delta not equal to 0, okay? Okay, suppose delta not equal to 0. Hmm? Suppose delta not equal to 0 and delta p equal to 0, what will happen? It will give you the same point. Okay. So therefore, delta naught, it doesn't matter. So if you add some error to here, like if your initial point is disturbed by delta naught, your final point is also disturbed by delta p. Okay, fine. So this is the idea. Hmm? So what can we do next? What should be our next step? What can be our next step? Hmm? Taylor series expansion. Taylor series expansion, isn't it? F of x plus h. What is f of x plus h? Like if you have a Taylor series, you forgot. What is it? F of x plus h time the derivative of x plus h square by 2 times double derivative of x. Like that, right? Yes. Yeah. So can we apply Taylor series to this? Hmm? Can we apply Taylor series to this? So what we will get? What you will get? Fp of, I wrote something mistake, is it? Yeah. See this and this. There is a mistake, right? Yeah. So x naught. Is there a mistake or no? Is there a mistake? You should find out. Okay. You find out. Hmm? So this is your exercise. Okay. Not assignment. Exercise. Okay. So you try to find out how to do Taylor series expansion to this. Okay. How to do Taylor series expansion to this form here. Okay. After you do the Taylor series, it will be better. I mean, you can lead, this can lead to the formulation of Lyapunov exponents. This can lead to the formulation of Lyapunov exponents. Okay. Fine. So let us come back to our main issue here. But here I just wanted to give you an idea. I mean, for any 1D map, how Lyapunov exponent computation works. You just perturb the initial point by a small amount, then you analyze how much big perturbation is happening to the final point, final iterate. Okay. What happens if your final iterate has been displaced by a lot amount as compared to initial point? What does it mean? Your trajectories have diverged. Yeah. If your trajectories have diverged, what does it mean? It means that it is chaotic. It means that it is chaotic, right? Suppose your trajectory has not diverged. I mean, equal distribution, equal way of perturbation is seen. Then it is regular. For periodic orbit, if you displace one point by something, the other point will be displaced by some amount. Okay, but it won't be like diverged. Okay, so in that way you can have a characteristic way of thinking about Lyapunov exponents. Okay. However, this one is the most important slide for Lyapunov exponents, where all the possible scenarios are discussed. Okay, I mean, if you have a 1D system, one Lyapunov exponent. If you have a 2D system, two Lyapunov exponents. Okay, three systems, three Lyapunov exponents. ND system and Lyapunov exponents. Okay, fine. So this is the idea. This is the idea so far. Okay, fine. So this is all about Lyapunov exponents, and you can compute the Lyapunov exponents in two parameter charts. Okay, which I showed you. Okay, so Lyapunov exponents is usually cannot be computed using your pen and paper. Okay, I mean, not like numerical methods or something like that. It has to be computed by feeding a time series. Okay, so input. So let us see. So input to compute Lyapunov exponent is a time series. Is a time series. Okay, let us is a time series. Okay, so the input is a time series. The longer, I mean, how much long can you iterate this? I mean, it can be 10 to the power of 6 steps. 10 to the power 6 steps means how much iteration? Think. 10 lakh. 10 lakh iterations. Yeah, 10 lakh. Okay. 10 to the power 6 steps is the input. Okay. And when you take the input, you feed the Jacobian matrix. Okay. Jacobian matrix. The Jacobian matrix, many a process will happen to the Jacobian matrix. Okay. And then it will output will be your Lyapunov exponents lambda 1, lambda 2, lambda 3, so on. Okay. Based on this, you can find the whether your system is chaotic or not. You can find. Okay. You can find. So this is how this plot was done. Okay. This is how this plot was carried out. I mean, where? Yeah, this is how this plot was carried out. When, and you can see over here, we can see over here, maybe this plot over here, why Lyapunov exponent computation is so much important. Okay, this is one of the slide which I used before. Okay, so this is what's the first top figure? Top figure is a bifurcation diagram. Top figure is a bifurcation diagram. What is the bottom figure? Bottom figure is the plot of Lyapunov exponent. Bottom figure is the plot of a Lyapunov exponent here. Okay, you can see. So what we see here, another important aspect you are going to learn in this slide is whenever a bifurcation happens, the Lyapunov exponent touches zero. Whenever a bifurcation happens, the Lyapunov exponent touches zero. Can you see this? Observe this one. Observe this point. Observe this point here. What is the bifurcation here? Period doubling, right? Can you see this here? So there are a lot of points. Maybe you can see this point. The Lyapunov exponent is touching zero. Even this point over here, this point here, you can see the Lyapunov exponent is touching zero, right? Fine. So yeah or no? Can you see? Can you see? Another point, can you take this nearby point? Take this nearby point. Again, it is touching zero. Take this point again, this one. Take this point again. Again, it is touching zero, right? So can you see the Lyapunov exponent is touching zero? Or no? Or shall we rub all of this? Yeah. Let us start. So can you see this point? What is this point? It's a period doubling, right? It's a period doubling bifurcation. Now corresponding to this point, can we stretch out a line? Yes. Oh, I mistakenly rubbed this. The line 0. This is our line 0. Yes. So can you see that this curve, yeah, exactly matches at 0, right? So whenever a bifurcation is happening, Lyapunov exponent is touching 0. And since it's a periodic orbit, the Lyapunov exponent is less than 0, below this axis. So the Lyapunov exponent is positive. Okay. The Lyapunov exponent is positive, right? So you can see, suppose these points, the positive points, these are the positive points, right? See, these are these points. All these points are above the axis, positive, and all these points are negative. All these points are negative, right? So these points you are seeing right now here, these are chaotic. These are all chaotic. Okay. However, the above points are all periodic. Okay. So through this Lyapunov exponent diagram, it can give you which attractor is chaotic, which attractor is quasi-periodic, like that. Okay. Fine. Okay. So this is what I wanted to show to you today. Okay. Similarly, you can study this. Okay. Same diagram. I think it's the same diagram. Okay. So whenever we draw a bifurcation diagram, a Lyapunov exponent diagram is better to have it side by side. Okay. So that easily you can see which point has negative Lyapunov exponents. Okay. Which point has negative Lyapunov exponent and which point has positive Lyapunov exponent. Okay. So the positive ones are nothing but chaotic. The negative ones here are nothing but periodic and very close to zero. See, these are very close to zero. So this is quasi-periodic. This is quasi-periodic. So this region you saw here, this region you are seeing here right now is nothing but quasi-periodic region, the yellow region here. Okay. However, the other region here are nothing but chaotic. These are all chaotic regions. Okay, these are all chaotic regions. However, these regions are periodic. These regions are nothing but periodic. Okay, these are periodic regions. Fine. So this is the idea. Okay. This is the idea of how you can understand the bifurcation diagram together with Lyapunov experiments. So one of the most important part of our course. So, but I have given you the, I mean, most important results. What we understand from this. Okay. So, however, other parts you can watch the lectures, how it is derived and those things. Okay. So those things I am leaving to you. Hmm? Fine. So we'll stop here. Hmm? So I hope you understood like how we compute Lyapunov exponents. Okay, we did not focus on how we will compute Lyapunov exponents because there are so many methods. Okay, so many methods to compute. However, there are ready-made packages available in Python where you can just call that function and feed the time series. It will give you the Lyapunov exponents. However, if you want to do it yourself, there are QR method available which you can use. Okay, so that is already available on web and all. But at least how many Lyapunov exponent, what is Lyapunov exponent spectrum? When a bifurcation occurs, Lyapunov exponent touches zero. Okay, in 3D system, how many Lyapunov exponents will be there? Okay, if it is close to zero, what happens? It's a quasi-periodic behavior. If it is negative, it's a periodic behavior. If it is greater than zero, it is chaotic behavior, right? So this property you should know. Okay. So from a time series, you can analyze this. Okay. So this is very related to time series. Okay. Lyapunov exponent, which is a quantitative measure to analyze all these things. Okay. Okay. So we'll stop here.